Hello and welcome to session 330 in the AISafety.com reading group. Tonight we'll be discussing Towards Guaranteed Safe AI, a framework for ensuring robust and reliable AI systems by David Davidat, Darimble and others. I find it instructive to start not with the proposed solution, but by starting to look at how Davidat conceptualizes the problem of AI safety. In this diagram, the AI is contained until it passes a proactive process-based quality assurance, after which it's declared safe and deployed. I think the process actually used in practice is better described as reactive quality control. So it's not quality assurance, but this might be maybe somewhat of a nitpick. The quality assurance primarily consists of evaluations and red teaming. And that's basically the entirety of the safety processes that are described to be inadequate. And I think, to be fair to the labs, they do in fact do more things. They are, like for instance, monitoring the actions that the AIs take. And I would also point to reinforcement learning from human feedback and interpretability as some safety measures that isn't quality assurance, but are more commonly described as being inside the AI. So this picture doesn't match reality, but maybe it does. It isn't necessarily true, because if you, for instance, conceptualize reinforcement learning from human feedback as just putting a mask on a Shoggoth, then this picture, I guess, is a reasonable visualization. I think I would also quibble that the pre-deployment containment that you can see here in faint yellow, that appears to be a very low priority for the labs. Okay, the central problem for this quality assurance process is that the AI is just fiendishly complicated, and we don't really have a method for figuring out what's really going on. And this is made worse by the sheer size of the AI. And that's strange, because in a sense, most of the AI probably isn't very relevant for safety. So size, complexity and opaqueness combines to AI systems where reasonable safety guarantees just are not available. And as a society, we have a right to safety, and we also have a right to some knowledge about the level of risk that we're taking on. And this is obviously something that I agree with so much, and I think it's so obvious that I won't really describe that part of the paper. Rather, and centrally, the point of the paper is that such safety guarantees are in fact possible to obtain. And that's the question I want to focus on. Is it in fact feasible to guarantee safe AI? Now let's look at the proposed process of getting quantitative guarantees for safe AI. So here we are replacing quality assurance that was done by humans with a computer program here called the verifier. And so the obvious problem here is who verifies the verifier and who verifies that process. And in a perfect world, what we'd really like is like a small human understandable proof that the AI in question is perfectly safe. This means that the verifier should be a computer program that, given an AI, creates a proof that the AI is safe. And if this proof is large and complex, then perhaps we could build a simple proof verifying program. And if it's that simple enough that humans can verify it by hand, then we've stopped the recursion. That's where it ends. And we have safety. One advantage of this that is unstated, but I think is important, is that this proof can potentially be generated by the AI itself. And that's of course really practical. It also carries a number of risks, and that's why I think it should probably be explicitly discussed. In practice, we may not get a perfect proof. We may only get a probabilistic worst case guarantee, and some of the process may not be like fully human understandable. So we might not get this, but something less. Okay, proving statements, that's kind of like a mechanical process, and we need to have some way to relate this to the actual world. So the proof should prove that the AI is safe, and that's obviously something that needs to be decomposed and spelled out. And this is formalized through what is called a safety specification, and this is also given as an input to the verifier, along with the AI. The safety specification is a mathematical, logical description of what effects are acceptable from this AI. And ideally, this should be based on a democratic process which determines what risks are acceptable and so on. For instance, the safety specification could be a formal description of the concept of harm and causality. What does it mean to cause harm? And I'd like to flag that causality is a part of the safety specification in Guaranteed Safe AI. It's not an obvious choice, but it's also not obviously bad. This would, for instance, allow us to specify Asimov's first law of robotics, that the AI should not allow a human to come to harm. But harm is an outcome, but what we get from the AI is only an output. So how do we bridge the gap from reasoning about AI outputs to reasoning about real effects? Well, to add the last piece of the puzzle, we need to introduce an explicit world model. This is given as another input to the verifier together with the safety specification. The world model models the world at a level of abstraction that is identical to the level that's used in the safety specification. And the model can answer queries on what happens in the world as a result of given outputs of the AI. This world model needs to be human understandable and one that we have a substantial degree of confidence in. This world model is potentially dramatically simpler than the full AI. For example, the rules of chess are much simpler than a good chess playing AI. And the axioms of mathematics are probably simpler than a theorem prover, and maybe for physics, natural laws are simpler than what they give rise to, right? So now we have the verifier, the safety specification, and the world model. And so we are ready to introduce the full Guaranteed Safe AI framework. We will list some desiderata in a moment. And the verifier can fulfill some or all of them. And thus we assign the verifier a level. In the paper, 11 levels are defined according to how strong guarantees the proofs and the verification can provide. The safety specification is also assigned a level, and 8 levels are defined, depending on how much safety they would grant if they are successfully implemented. Correspondingly, the world model is also giving a level. 6 levels are defined, depending on how much safety they would grant if they are successfully implemented. That did sound like a copy-paste error, but it might not be. Like, I'm unsure precisely how a good world model in itself would provide a level of safety. But given these levels, any implementation of an AI system can be classified, even if most of them have like level 0 on, so V0, S0, and W0. The authors reserve the term Guaranteed Safe AI for systems that are at least V8 and S3 and W2. Let's start by looking at the verifier and at the levels of verifiers that are defined. So the 11 levels of the verifier can actually be split in 2, at least as I see it. So we'll start with the bottom 6 levels. In my conceptualization, the first 6 levels are steps towards doing the right thing, and the subsequent levels are about doing them better. So the 0th level it's a verifier that doesn't try. It outputs the null proof. The first level is a verifier that is some ad hoc testing that probably isn't very automated, that are providing heuristic-based assurance, as it's called euphemistically. The second level is roughly where we're at, with standardized tests that could in theory be audited by third parties and compared, though this isn't something that's done in practice. At the third level, we automatically introduce new tests given some kind of template that is randomly populated to get dramatically larger coverage. Fourth level is some kind of automated red teaming with back and forth between the verifier and the AI. This is called black box fuzzing. Next, we have white box fuzzing, which is kind of like black box fuzzing, but now the red team has interoperability and explicit targets exposing unsafe internal states. Now let's look at level 6 to 10, which I claim is more about doing like this kind of box fuzzing better. But this isn't entirely correct, because level 6 regresses to black box fuzzing, but adds some criteria that we must eventually find all behavior. I think it's kind of strange, really. I think it's a bad level, because there's a lot more safety in white box adversarial testing, and having asymptotic bounds like might not be that important because they're likely to be very bad. Level 7, however, is white box fuzzing. And again, we also have a formal guarantee that if the AI is unsafe, the verifier will eventually uncover this. But also, the white box fuzzing means that we check unsafe areas first. Level 8 makes these kind of convergence bonds non-asymptotic. And that's, of course, really great. I would have preferred to call them practical, even though that is less precise, because like this is reasonably informal anyway. And what matters is that this kind of, like, we can practically ensure that the AI is safe. Level 9 gives us a more complete sound bound on the actual probability of failure. And then level 10 makes the proof human checkable and compact enough to be that. Creating such a verifier seems like a really tall order. In particular, for testing software, formal verification is known to be hard and time-consuming even for small projects. And the authors acknowledge that they're trying to do something that is more difficult than verifying a small software program. I really want to emphasize that they are trying something that is much, much more difficult. The authors suspect it might be possible to train a narrow AI as the verifier, and I think a priori that sounds really hard, because like I've been doing a bit of red teaming, not very much, but it feels like it's something that strongly relies on having general intelligence. The authors also point out that the train data for the verifier could plausibly be extracted using AI that's pretty unsafe. Whether the verifier could be built is intuited to rely centrally on the degree to which it's possible to decompose the AI. And my intuition is that it is in fact usually not possible, like superposition and all that. And like if it turns out that this is not possible, well, like then what? That was the verifier. Let's turn to the safety specifications. So recall that the Guaranteed Safe AI framework defined 8 safety specification levels. They are sorted by how much safety they grant according to the authors. However, when I read them, it seems like much more about how human auditable the levels are. The 0th level, again, is the null level. And the first level is a pool of humans using their high-level judgment as to whether this is safe, but that's not really automatable. It also isn't understandable, because at some level, humans are black boxes, kinda, if you squint, maybe. But level 2 is a natural language specification that is fed into a neural network, which then evaluates this. So, yeah, level 3 move some of the most important logic to a level where humans can audit and participate, where this is possible. Level 4 is a safety specification in a system that's like fundamentally logic, but do contain some learned parts, in particular in the binding to the physical world. Level 5 is a totally descriptive safety specification, but one that the AI have generated. Humans have only audited and perhaps only audited it incompletely. Level 6 is then this comprehensive human-constructed formal safety specification. There's a level more, level 7. I'm a bit confused. It's like everything is just same as 6, just more broad. Maybe it kind of feels like our coherent extrapolated volition. Like I feel level 7 is very unlike the others, and since level 6 is what we want, I would just omit level 7. Okay, how do the authors propose that we go about making safety specification? Like, I should admit my logical training ended with Jane's probability theory, so I can only really offer a brief, this seems really, really hard. So yeah, this seems really hard. And the difficulty is increased by the fact that the specifications need to slot into the formal verifier and also the world model. Part of the solution is probably a utility function, but you need to have more than just a utility function. I'm personally interested in this topic. I wish that this was explored some more. The safety specification itself needs to be compact, and it can't do things like an unbounded maximizing safety or something like that. We might need to use proxies, but of course using proxies is subject to Goodhart's law, so that's really, really non-trivial. So what do I think? I think, like, my personal central conclusion is that safety specifications become more tractable the smaller the domain is. There isn't really a good reason to look much outside Nick Bostrom's 6 strategic cognitive domains. So by restricting the domain, it may be easier. It may in fact be possible to at first focus strongly on just corrigibility, because that may in fact be sufficient, and that is a lot easier than, everything. After the verifier and the safety specification, the time has come to the world model. As before, the framework defines 6 levels of world models by how much safety they provide. My definition on the levels, which the authors may not endorse, is how easy is it for an AI to find a loophole in the world model. So the 0th level, as always, is not even trying. That's like what we're doing now. The first level is training an AI directly on the data, as in model-free reinforcement learning. Second level is where you use a machine-learned generative model of probabilistic causal models and test whether this agrees with some other human-made models. Third level is world models that are fully audited by human domain experts. And fourth levels are formally verified models that are based on abstractions all the way down to physical laws. Fifth level, that's a safety system where the AI is proven to be safe in all possible worlds, and so you don't need any world model. Again, I feel this level doesn't really fit into the framework and probably should be skipped. Also, I feel like it's not a fair characterization of agent foundations. They don't include all possible worlds, right? They make some assumptions that could make it tractable, like at least induction, right? Let's look at how the authors propose to actually make this world model. One crucial factor is modeling humans, which is important for safety, and humans are also important because they are strategic actors. There may be a fundamental trade-off between interpretability and accuracy, and the world model also needs to handle both known unknowns and unknown unknowns. One uncertainty that I feel the paper did not resolve is, if we have a lower resolution, what certainty can we get? Can we omit butterflies? You would think you could omit butterflies from the physical world model, but then you may not be able to predict the weather, right? And the authors seem to have a procedure in mind for finding the areas that you can disregard, but it's really underspecified, and I think this is crucial. I think part of the answer that the authors would give is to just say, this is uncertain, label it as uncertain, and then just work from the worst case. But I feel the worst case is almost always unacceptably bad. And that means that the verifier will predictably fail if there is substantial uncertainty. I wanted to show this. It's a large diagram of how a lot of other AI safety proposals fit into this framework. I really appreciate the effort that's been taken in this regard, though I won't have time to go into details here. Instead, let's turn to feasibility. Is it practically possible to build guaranteed safe AI? There's a lot of musings about implementation, but I'd like to focus on one of the principled reasons why world models would be simple. The argument goes, AI is only really dangerous if it's exceedingly intelligent, and you can't be very intelligent if you can't make a strong world model. But if the AI can make simple but very predictive world models, well then presumably so can we, right? So if AI risk is very high, then the tractability of making world models is correspondingly high. It's a cute argument, right? But most of guaranteed safe AI is actually not so much about the predictive strength of the model, but more about like how interpretable they are. Another argument is that if guaranteed safe AI doesn't work, well, then nothing works, because if we can't make good enough world models to satisfy our specifications, then the strength of any verifier is irrelevant, or indeed any quality assurance scheme, and basically AI safety is impossible in general. I don't think that follows. Like, there's a lot of incidental decisions in the design of guaranteed safe AI, and these could be loosened. So my actual true suggestion is that if it turns out we can't make AI safe in this world, then we should not build it. Which in practice probably means delaying until you can make AIs that are safe in any reasonable world, which is like, agent foundations. I'm going to skip over more and skip straight to the author's conclusion about the feasibility. And David is open about the technical challenge, which are described as serious. The three main challenges are creating accurate and interpretable world models, formulating precise safety specifications, and performing formal verification at scale. However, the authors clearly state that other methods are substantially worse, and that makes guaranteed safe AI a necessity in spite of the challenges. What are my personal conclusions? First, I would say that I think this is great work in how it evenly cuts a hard problem, this quality assurance, into three easier problems: the verifications, safety specifications, and world models. And I feel it cuts reality at the joints in a very powerful way, and I really like that. The biggest red flag for me is the examples that the authors use, which are invariably like narrow tasks. And I don't really care about that. I want to know if this is something that could work for ChatGPT. I think my reservations on feasibility are not well described as serious. I think my reservations are much, much greater than the authors. And like many of the conservative assumptions seem to me to lead directly to like, you can't prove this, and then what's supposed to happen? The safety specification in particular seems deeply entangled in what is sometimes called good old-fashioned AI. And it feels like we've been trying to do something like this for 40 years and failed. For instance, like the formal verification looks really difficult to me, but the authors include some people who are like cream of the crop researchers on this specific field, right? And I imagine like if I'm having a conversation with some of these people, then I think they would be able to answer me pretty well. So I should update to be more positive on this. On the strategic side, I think this paper is very helpful because pausing AI is an easier ask if we can point to what we can do in a pause. And this is in fact something that we can do, right? I would prefer the framing to be more explicit in preventing safety washing. I don't want OpenAI to say that, oh, we are level 2 guaranteed safe AI. And I actually feel that even the minimum levels to be guaranteed safe AI, that was verifier level 8, safety specification level 3, and world model level 2, that isn't that good. That appears to me to involve a very substantial risk. And also, like from a the fact that the authors are very prestigious seem to be something that will like improve the impact substantially of this paper. That concludes my presentation on Towards Guaranteed Safe AI by David Dalrymple and many others. Thank you for your attention and see you again on the 27th of March. Ceterum censeo machinam sapientem esse delendam.